Welcome to episode 7 in Topics in ECE. As you can see from this cover slide, there's a lot to talk about today. A main focus is going to be on logarithmic scales and also on dB. And you may have met these in audio, such as music. And in fact, that's perhaps one of the primary places where these things come from. Music involves frequencies, of course, the waveform here has a particular frequency, and amplitudes, but the frequencies are harmonically related. What that means is there's a C note here, but there's another C note up one octave higher that's twice the frequency, and then there's one up even higher than that that's 4 times the frequency. So the concept of log scales presents itself naturally. Down here at the bottom, we'll go into this in some depth, but you can see the audio frequency spectrum, and you can also see radio waves up here. And in order to fit all those frequencies, which is like 12 orders of magnitude on one plot, we use what's called log scaling. And dB, or decibels, is used for the same reason. And we're going to start by focusing on the audio spectrum because it's familiar, but also because that's where a lot of these concepts basically come from, the concept of a decibel. So let's get started with the audio. This is pulled from episode 4 in this series. And if you've watched some of those prior episodes, you know that a main focus of these series, given that it's electrical and computer engineering topics, is circuits. So we're going to talk about this just for a moment. I just wanted to walk us through a quick review. This is obviously a guitar amp, and this is a schematic of, not this guitar amp, this is a pile. This is a guitar amp from Ampeg, but it'll serve our purpose. What does a guitar amp do? Well, obviously it amplifies, it makes the sound really loud, but it does more than that. It changes the tonal nature of your guitar. And that has to do with frequency response, which is affected by all these components that we see here. All of these changes in the signal, the amplitude being increased, the frequencies being selectively attenuated by this circuitry here and so forth, is what I call signal processing. In this case, it's audio. But as we said, the signal processing involves more than just audio. We had to get rid of some of the radio frequency interference. And we did that with a low-pass filter, which is primarily composed of R1, this resistor, and C2. And that's a circuit that we've been studying in some depth. Indeed, if you watched episode 6 in this series, the previous episode, we talked about it in a lot of depth, using mathematics, complex numbers, phasors, and we were examining just this basic circuit composed of a resistor and a capacitor. And we derived this so-called transfer function. And ultimately, we came up with a graph that shows how the output signal amplitude is affected by the low-pass filter, which is what this RC circuit is. And using the complex numbers and phasors and all of that good stuff, we could write this expression right here. The output voltage divided by the input voltage, the so-called transfer function, if we look at just the magnitude of it, it is given by 1 over 1 plus f over fc squared, and then you take the square root of all of that in the denominator. And you plot it out, and then it's a whole lot more easy for most people to grasp because you have a graph. And this graph tells us that at the corner frequency, so-called corner frequency, which is given by 1 over 2 pi RC for that particular circuit, the amplitude of the output is a little bit less than the amplitude of the input. At lower frequencies, the ratio is 1, so the output and the input are about the same amplitude. But as you go up and you hit the corner frequency, we're down to 0.707. And some of you may recognize that as 1 over the square root of 2. And where does that come from? Well, if you stick in fc for your frequency that you're dealing with into this formula, you have fc over fc, which is 1. And you square that, you get 1. And then you have 1 plus 1, which is 2. And so the result is 1 over square root of 2. All right. So that's what all this math tells us. But we're also trying to understand what happens at the high frequencies that we're trying to get rid of, those radio frequencies. So let's say we double the frequency. We're still in the audio range, but let's say we double the frequency so that f is now 2fc. So this would be 1 plus 2 squared, which is 5, Square root of 5 is, oh, I don't know that one off the top of my head. Oh, I just punched it in my calculator. It's 2.23. So at twice the frequency, we have 1 over 2.23. So the voltage has been divided by about a half. In other words, the output voltage is about half of what the input voltage is. So we'd be about here, right? About 0.5. At 2 times F, oh, wait a minute. FC is here. 2 times FC should be way over here, about twice the distance from the origin. So this question down here, is the frequency axis linear or log scaled here? Clearly, this is not a linear scaling. So obviously, it must be log scaled. So that's my lead into this slide on linear versus log scaling. A linear scale would be something like this at the top. The origin would be 0 hertz, and then maybe 100 hertz and 200, and then 300. Oh, wait, I have a little break here. So I figured out automatically that I wasn't even going to get up to 1 kilohertz on this scale. So I did a break, and, well, if I'm on the same scaling, then now I can call this 1 kilohertz, but then this would be 1.1, and 1.2 would be here. Oh my, even 2 kilohertz is way off this slide to the right. And 20 kilohertz is way, way off the page. So that's why we use log scales, like this one. We can compact like 12 orders of magnitude in frequency into a scale that can fit on a single page. Even if we're just interested in audio, we still have to use log scales. And many of you have probably seen audio circuit or speaker data sheets and seen these logarithmic scales on them. But why is it called a log scale? If you look at the numbers on here, we've got 10 to the 1, 10 to the 2, 10 to the 3, 10 to the 4. So this is 1,000, this is 10,000, and so forth. So they're going up by factors of 10. It looks like an exponential. In fact, it is going up exponentially. So why the heck is it called a log scale? Well, if you take the logarithm of these numbers and you do another axis down here, and you just put the logarithm of those numbers on this new axis, this would be labeled 1, this would be labeled 2, 3, and so forth. And here I've labeled it log base 10 of f. And that's what these numbers are. They're the logarithms of the frequencies. And we could take graphs like this, and we could label the horizontal axis with the log of f. And then we have numbers like 1, 2, 3, 4, and so forth. But it wouldn't be terribly meaningful. It's much more meaningful to write the real frequencies on the axis. Now, before we leave this slide, I want to point up a couple of other important things. Focusing in on the audio section, which is 20 hertz to 20 kilohertz by most people's accounts. Speech is confined to about 300 hertz to 4 kilohertz. If you just are able to pass that frequency range, then people can understand what you're saying, and more importantly, they can also understand who's saying it. But if this coordinate is 100 hertz and this coordinate is 1 kilohertz, 10 to the third, where is 300 hertz? Well, you might think it's 1/3 of the way from 100 hertz to 1 kilohertz because it's 300 hertz. But no, it's actually halfway. 300 hertz is almost exactly halfway between 100 hertz and 1 kilohertz. How do we justify that? Where does that come from? Well, let's look down here at the bottom. Remember, this underlies the scaling on the graph. And the log of 100 is 2, and the log of 1 kilohertz is 3. It turns out that the log of 300 hertz is very close to 2.5, right in the middle. So that's where that comes from. So that's frequency. Let's move on to amplitudes and decibels, or dB. We're going to present the usual equations in terms of 10 log to the base 10 of something or 20 log to the base 10 of something, but this is not math on this slide. What I want to talk about here is what is dB in audio? Well, as you probably know, it's an assessment of how loud something is. So here I have a speaker, and it's creating sound waves that then reach an ear. And your ear then takes that and transmits information on frequencies and amplitudes to your brain. And that's how we hear music or speech. In the world of physics, we think about the sound pressure level of the wave itself. This is compression and expansion of the air between the speaker and you. So these are pressure waves. And the pressure is measured in pascals. But the concept of dB kind of originated with Alexander Graham Bell, hence the decibels. And he was exploring the human sense of hearing. And he looked at the relationship between sound pressure level and the perceived loudness. And what he found was, if you increase the power in the acoustic wave by a factor of 10, it sounded twice as loud. And that was called 1 bell. And then if you were to, say, crank up the power by another factor of 10, so it was 100 times as much as the original, then it would sound twice as loud as the previous one, which is 4 times as loud as the original one. Hey, you can kind of see some exponential / logarithmic behavior going on here, right? Anyway, that would add another bell. But we decided, I don't know who decided it, somewhere along the way, that we wanted some subunits. So instead of talking about bells, we talk about decibel. A decibel is 1/10 of a bell. So it takes a 10 decibel increase to be perceived as twice as loud. So that's something to be remembered, and you can look up a lot of this information in Wikipedia. That's where this diagram is coming from. And I've added another couple of bullets here for us audiophiles. Sound pressure level decreases about 6 dB every time you double the distance from the source. So if you take your ear and you move twice as far away from the speaker as where you were, then it's going to go down by 6 dB. The other point to note is that speakers are typically rated about 1 meter from the source is where the measurement is done, and they're rated at 1 watt. So let's take a look at a couple of data sheets for speakers and see what that means. So these are a couple of speakers from Radio Shack that I had when I was teaching the Intro to Electrical Engineering course. And here's a crossover network that we also passed around as kind of show and tell items. The woofer, of course, is the low frequency speaker, and the tweeter handles the high frequencies. Let's take a look at the graphs now and put all this stuff that we've been talking about together. This is a 4-inch woofer. It's not very big. So you can't expect a whole lot of bass out of it. Well, let's take a look at the graph and see what it does. The marketing department, of course, labels this as having a frequency response from 50 hertz to 7 kilohertz, but that doesn't mean much. We need to look at the graph to really understand it. So when I look at this graph, this axis is decibels. That's the sound pressure level measured at 1 meter from the source. You can see that here. Sound pressure level 84 plus 2 dB per watt at 1 meter. What does that mean? Well, I think this is an error. I think this is 84 plus or minus 2 dB for manufacturing tolerances. And the per watt, I hate that notation. That's not real. That means for a 1 watt source. So let's just call it 84 dB at 1 watt at 1 meter. At what frequency? Well, again, let's go over and look at the graph. So it looks like by the time we get to 200 hertz, we're pretty close to that 84. This is 80, this is 90, so 84 is close to the middle, so we're talking about basically a line right here. So 2 or 3 dB down from that, maybe we're at 150 hertz or something. So I'd call this 150 hertz to 7 kilohertz speaker. It'll do some 50 hertz and some 20 hertz, but look, at 20 hertz, you're down 20 dB, 25 dB almost, from 85 down to 60. So that's pretty quiet compared to the mid-range of the speaker, which starts arguably around 150 or 200 hertz. And then we can see it goes up to at least 5 kilohertz or a little more, and we'll call this 7. So yeah, 7 kilohertz good, 50 hertz not so much. Now these sound pressure levels are at 1 meter away from the speaker, which is kind of reasonable, and they are at 1 watt. This speaker can handle up to 10 watts. And so how many more dB would we be then? Well, we'd be about 10 dB because it would be 10 times the power. So instead of 84 dB, we'd be at 94 dB. Okay, so how loud is something like 84 dB or 98 dB? Well, it's within the range of human hearing for sure, because by definition, 0 dB is almost silent. That's the weakest sound an average human can hear. That's the definition of 0 dB. We can definitely hear sounds up to 100 dB and even louder, but it gets a little dangerous as you go beyond 100, and in fact it can get very dangerous once you get up above 120. So caution, danger. Levels above 120 dB at the ear can cause immediate hearing loss. Now 140 is probably not going to make you deaf immediately, but it will degrade your hearing so that in the future you won't be able to enjoy stuff as much anymore. So avoid things above 120. And in fact, long-term exposure in the 100 to 120 range can cause hearing loss over time. And I got this from a CDC webpage. But back to this graph. I colored the 0 to 80 range, or the 0 to 100 range, in yellow here. That's the kind of normal range of sound levels that you're exposed to in normal life. At a football game or something, if you're in a really loud crowd, 120 you might get to. I don't know, it might get to more than that. I wear earplugs at football games myself and at concerts and things like that. Now, in the physics world, remember sound pressure level is in pascals. So let's move back from dB world to the physics world. 0 dB, remember that was defined as the weakest sound an average human can hear. Turns out that when that was measured, it was 20 micropascals, 20 millionths of a pascal. And you can see the corresponding relationships here. Every time you go up by a factor of 10, say from 20 micropascals to 200, which would be about here on a log graph, 200 micropascals, that's actually a 20 dB change. So this is a little weird because previously I was talking about factors of 10, adding 10 dB. That's in power. This is a sound pressure level. And here's the formula for converting from sound pressure level to dB. You take the ratio of the sound pressure level you're interested in, say 200 micropascals, to the reference level, the 0 dB point, that is 20 micropascals, so this number is 10. So we take log base 10 of that. Log base 10 of 10 is 1. And then you do that times 20, and that means you're up 20 dB. So that's why we went from 0 to 20 when we only went up by a factor of 10. In sound pressure level, very confusing. But this is the same thing that happens with voltages in a circuit. Voltages, when you go to dB, are like you use 20 log, whereas for powers you use 10 log. But the main point to be made is that we're using logarithms here again. And that's because human hearing evolved to allow us to hear way big orders of magnitude changes in sound levels. From 20 micropascals up to at least 1 pascal, and maybe a little higher if you want to risk your hearing, and certainly do not go into this range. Air pressure level on Earth is 1 atmosphere, so that's 100,000 pascals. That would create deafness immediately, of course. In fact, these numbers will here as well. But this is the loudest so-called sound possible. But again, the point is the human perception system is capable of looking at sound levels over a huge range, orders of magnitude. And that's why we use dB. Here's a couple of references or internet links that I used in the creation of this video. One is the CDC page here about hearing loss, and the other is the Wikipedia page. And here's a statement on the Wikipedia page that's worth reading. The human perception of the intensity of sound and light, so this applies to the visual system as well, more nearly approximates the logarithm of intensity rather than a linear relationship, making the dB scale a useful measure. This Wikipedia page also goes into some information on acoustics. They have that formula that I just presented here. And they talk about the difference between that and when you're dealing with power. And here's a nice table from that Wikipedia page. I don't want to spend any time talking about this, so if you want, you can freeze it here and maybe look over it. But I would say that this is worth looking at and studying. 0 dB is a power ratio of 1. It's also an amplitude ratio or pressure ratio of 1, whereas something like 6 dB is a power ratio of 4 or an amplitude ratio of 2, blah, blah, blah. Anyway, have a look at that. Think about it. Let's move on. Remember, our main focus today is on logarithmic scales. But now we have dB, which is also a logarithmic animal. And there's something called dBm, which comes into play when we're dealing with radio. So in our next couple slides, we're going to return to this low-pass filter circuit and cast its response in terms of dB versus log frequency. And after that, we will look at the use of these concepts in radio and microwaves. So here's our basic low-pass filter that we examined in some detail in the last episode, episode 6 on complex math. And we came up with this expression for the transfer function. H of f is called the transfer function. It's the thing which you multiply the source voltage by to get the output voltage. This is the source voltage. The output voltage is here. And it's a function of frequency, as we know. And the graph shows us what that function is. Now in this graph, I've actually labeled a log scaling of frequency here, 0.1 FC, FC, 10 FC. Remember, FC is the corner frequency. And I picked some values that came from our previous episode in the series, 1K and 160 nanofarads, to give a basically 1 kilohertz corner frequency. So in addition to labeling it as shown here, I've actually put 100, 1K, and 10K hertz. And from this graph, we can now read off some useful values. For example, if we just looked at it, we could say, oh, this is a 1 kilohertz low-pass filter because we're down to 1 over the square root of 2 at 1 kilohertz. We can also read off, more or less, the value that we get at 10 kilohertz. At 10 kilohertz, we're here. Come over to the left-hand side. I don't know, that looks like about 0.1, if this is 1. And down at 100 hertz, we're clearly very close to 1, maybe 0.99 or something. But it's that or something which leads us to maybe wanting to change the vertical axis scaling as well. And here I've put it into Excel in order to make some nice graphs. And the first graph is h of f, the transfer function, versus frequency on a linear scale, which we already know we probably don't want to be doing. And now you can see why. On a linear scale, in order to go all the way out to 100 kilohertz, which is what I wanted to do here, it compresses all the useful information, what's going on in the passband and slightly above the passband, it compresses it all into that dot. So all the frequencies we care about almost are down here. But now we, of course, know that we should logarithmically scale the frequency axis. And if I do that, which in Excel involves right-clicking on these numbers here and then selecting log axis, I get this. And what do I see now? Well, I can clearly read off that at 1000 hertz, we're right here, and that's about 0.7, which is what we know it should be. And at 10 kilohertz, I'm here, and that's about the 0.1 that we estimated from before. We still, however, cannot read off a decent value at 100 kilohertz. So what should we do? Well, this was a linear scale in frequency. This was a log scale in frequency, and it's called a semi-log graph because only the frequency axis, only the horizontal, has been log scaled. What if we log scale the vertical axis by right-clicking on these numbers and selecting log? Well, in that case, we would get a log-log graph, look something like this. And now, at 100 kilohertz, I can read off that I'm right here, and it's in fact 0.01. I could not read that from this graph, but I can from this one. So that's why we like to do a log scaling. on the vertical axis in this case too. Let's pick another number. This is 20 kilohertz. And so at 20 kilohertz, where am I? I am over here. This is 0.01, this is 0.02, 0.03, 0.04, 0.04, 0.05 it looks like. I couldn't really read that accurately from this graph. I know that's 0.1. Yeah, maybe you say that's 0.05. But this new graph scaling allows us to read the numbers way out here accurately. So here we're log scaled on both axes, and so it's called a log-log graph. Finally, this one may look pretty similar to what we saw a minute ago when we had dB, and in fact it is. I've plotted it in dB here. So now I'm not log scaled here. I simply created a new column of data in the Excel spreadsheet where I computed the dB using this formula. Remember, H of F is a voltage ratio. And when I convert a voltage ratio to dB, I use 20 log of that ratio, just like I would with the ratio of the sound pressure level to the reference level of 20 micropascals. I would use 20 log there. Here I'm using it for the transfer function. So this returns to a semi-log graph because I'm plotting dB in a linear scale. One final and very important note from this slide is the slope of this curve. Look, this looks quite linear. Looks like a straight line, that is. And we can figure out what the slope is. Now, if you were to take this straight line and run it all the way up to here, which is the corner frequency, then you could make a plot that has two straight lines, one here and then one here. That's called a Bode plot. And on a Bode plot for this filter, the response falls off as minus 20 dB per decade. Every time we go out by a factor of 10 in frequency, we fall by 20 dB. So from here to here, so we fell by 20 dB when we went from 1 kilohertz to 10 kilohertz. Then if we go from 10 kilohertz to 100 kilohertz, we fall another 20 dB. So now we're down to minus 40 dB. That's a very useful thing to remember. In fact, we could apply it again and say, okay, well, what happens if we went from 100 kilohertz to 1 megahertz? Maybe you're trying to reject some radio frequencies or something. Well, then we'd be down another factor of 20 dB. So we'd be down at minus 60. Another useful tidbit to remember is that the roll-off is minus 6 dB per octave. Every doubling of frequency, you're falling 6 dB. So for example, from 10 kilohertz here to 20 kilohertz, you go from minus 20 to minus 26. But note the asterisk. These are for what's called a single pole filter. That's because there's only one R and one C here. More involved filters can roll off faster, like at minus 40 or minus 60 dB per decade. But they're more complicated than this filter. Okay, so that covers our main topics except for dBm. Let's take a very brief tour of how you apply some of this material in radio frequency applications. Here there's a satellite around the planet Mars, and it's beaming a signal back to the Earth. And here's a huge dish antenna, like a big ear for radio, trying to receive that signal. And I claim that the signal we get back is minus 110 dBm. What is that? What does that mean? Let's have a look. On this channel, we also have an antenna briefs series. And this is from episode 3 in that series, titled Maximizing Range. Here's a diagram that shows a transmitter sending out a radio signal, and then a receiver over here picking up that signal. And if you go to Antenna Briefs episode 3, we'll walk you through where this formula comes from and what this all means. But in a nutshell, whatever radio frequency signal power you feed out to the transmit antenna goes out into the universe and starts spreading out. And by the time it gets over to the receiver, it's a lot weaker. And that's because that power has been spread over a huge sphere. And so with the receiver, we think about something called power density in, for example, watts per square meter, or maybe femtowatts per square meter in reality. The equation we worked out in this episode 3 is the transmit power times the transmit antenna gain. So if you're focusing the power with a directional antenna, you have another factor up here in the numerator, divided by 4 pi d squared, where d is the distance between the transmitter and the receiver. So d, as it goes up, the power falls by the square of that. In fact, for what's called terrestrial use on the planet Earth, when we're using our cell phone and stuff, this so-called path loss exponent can change from 2 to something like 3 or 4 or 5, and the power falls off drastically. So suffice it to say that the power density at the receiver is really weak. And how do you get the power into the receiver? Well, you take that density and you multiply it by the effective area of the antenna, which, for our case of the dish antenna, is the area of the dish. This is a 70-meter diameter dish, so you can work out the area. And when you do that, you will get some number like 1 times 10 to the minus 14th watts. That's 10 femtowatts of received power. Really, really weak. And for similar reasons to audio, we often put this on a dB scale, and it's on a scale called dBm, dB relative to a milliwatt. So here is that formula. The power received in dBm by a radio is 10, because it's power, 10 log of received power divided by 1 milliwatt. Received power relative to a milliwatt. So for the case of an orbiter around Mars sending a signal to the 70-meter Goldstone dish in California, we get 10 femtowatts of power, which is about minus 110 dBm. These are just numbers that are easier to work with. And I'll refer you to episode 3 in the Antenna Brief series for a more lucid explanation of all of this. Finally, for terrestrial links, as I said, the so-called path loss exponent in this formula changes from 2 to something like 3, 4, or 5. 4 is often taken as a nominal value for how quickly the power decays as you leave the transmitter as it winds its way to the receiver. Here, the students in our class took some readings. We had a transmitter, we're walking around with it, and we had a receiver here in the communications lab, and we measured the signal powers we received at various distances. And we did that for several different frequencies, and you can see some of the numbers here. This is at 151 megahertz, which is an unlicensed band. And the received power varied from about minus 20 dBm to less than minus 100 as we got out to about 2 kilometers away from this receiver. So for that, we had to leave the building and go out here in the parking lot and beyond. But that was at 151 megahertz. At 2.4 gigahertz, which is where Wi-Fi tends to work, the powers roll off much faster. And the maximum range we're able to get is about 200 meters. This break right here is where we had to leave the building, and we're now down in the parking lot. But you can see some of the path loss exponents, 4.2 and 4.8. These are just best fit lines. Okay, that's it, except cell phones. If you've got everybody has a cell phone, right? So they're the modern Swiss Army knife. You can do just about anything with them. If you're interested in seeing how strong the signal your cell phone is receiving, then you can usually find the signal strength buried somewhere in the settings menu. This is for an Android phone, and so I selected the settings guy here, and then at the bottom of that menu there's something called About Phone, and near the bottom of that there's something called SIM Status. And I clicked on that and looked down here, and I found signal strength, minus 99 dBm. So that's a pretty weak signal. Sometimes you'll see minus 80, sometimes you'll see minus 110 or even less. But by the time it gets to minus 120 or minus 130, you're probably not receiving any more. In the world of audio, there are also some fun things you can do with your cell phone. I found a couple of apps, one called Sound Meter and one called Sound Analyzer app. And these can measure sound pressure levels, although, caution, some of these apps may be inaccurate, especially at loud sound levels. So do not use them to find out if sound levels are safe. But they're fun to play with. This Sound Analyzer app even has a spectrum analyzer, an audio spectrum analyzer. It's only 1/3 octave band, but it might be fun to play with. I'm actually thinking in the next episode we probably get into spectrum analysis and Fourier series and Fourier transforms. So this kind of leads into that. Until then, thank you for watching this episode, and I hope it's been useful to you.